All right, let's dive right into this highly requested explainer. We're going to completely break down the exact mechanics behind a function calling itself multiple times. Now, if you've been writing recursive code, you've totally got the hang of a single function looping back on itself, right? It's pretty standard. But what actually happens under the hood when one single function branches out into 2, 3, or even more parallel paths? Well, that's exactly what we're going to demystify today. To keep us from getting lost in the weeds, here's our really quick roadmap for today's explainer. Beyond single recursion, the Fibonacci formula, the waiting room stack, tracing the recursion tree, and finally, exponential time complexity. Let's get to it. Section 1. Beyond single recursion. So the absolutely crucial thing to grasp here is the massive jump in complexity. We're going from a simple loop-like single recursion to the crazy branching pathways of multiple recursion. With single recursion, it's honestly a straight line. Your function does some work, calls itself, maybe does a bit more work, and eventually stops. Simple. But with multiple recursion, a function might call itself twice or even n times right inside its own logic. Suddenly, you aren't just walking down a hallway. You're navigating a rapidly expanding maze. Section 2. The Fibonacci formula. To really wrap our heads around this, we need a solid anchor. And honestly, there's no better example than the classic Fibonacci sequence. What's so beautiful about this is how incredibly simple the core math is. It's built on a super basic rule. You just take the last two numbers you generated, add them together, and boom, you've got your next number. If we actually map out those first few numbers, the pattern is impossible to miss. We start with 0 and 1. Add those, you get 1. Then 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, and it just keeps going. It's elegant. But if we want to ask our computer to find, say, the nth Fibonacci number, we have to translate that clean mathematical logic into a recursive algorithm. Algorithmically, here are the exact steps our code has to take. Step 1 is our safety net, our base case. If n is 0 or 1, we just return n and stop. Step 2 is where things get interesting. We create a variable, let's call it last, and assign it the recursive call of n-1. Step 3 is our second recursive call, assigning n-2 to a variable called second_last. And finally, step 4 just returns the sum of those two. Notice the catch here? Inside one single function, we're making two completely separate recursive calls. Which brings us to section 3, the waiting room stack. Now, how does a computer actually process those two side-by-side calls without just breaking? You have to remember the golden rule. Computers process code strictly line by line. It's so tempting to imagine the computer branching out and magically doing both n-1 and n-2 at the exact same time. But they don't. The computer handles the very first call it sees and literally pauses everything else. I like to think of the stack memory as a literal waiting room. The right side of our equation patiently sits there, reading a magazine, while the left side dives deep into its own execution. When the code hits that first recursive call for n-1, the entire function freezes. The n-2 call hasn't even been looked at yet. The computer just plunges down that n-1 path, creating new instances until it finally hits a base case. It only moves on once it gets an answer back. Section 4. Tracing the recursion tree. Let's actually trace this journey chronologically for the fourth Fibonacci number, or f of 4. Following the leftmost branch down, f of 4 needs f of 3 and f of 2. But keeping our golden rule in mind, it completely pauses f of 2 and dives straight into f of 3. Inside f of 3, it needs f of 2 and f of 1. Again, it pauses the right side and dives into f of 2. Inside f of 2, it needs f of 1 and f of 0. It dives into f of 1. We're going deeper and deeper down this vertical path, and literally nothing has been calculated yet. But then we hit rock bottom. The base case is, because any n less than or equal to 1 returns itself, our program finally stops diving. It can turn around and start bubbling answers back up the tree. This is the turning point where the stack memory starts waking up all those frozen waiting functions. First up, that bottom f1 call finishes and hands back a neat 1. Because that f1 resolved, the f2 function can finally wake up and process its second line of code, calling f0. The f0 call immediately hits the base case, finishes, and hands back a 0. Adding the 1 and the 0 together, our f of 2 calculation officially resolves and bubbles up a 1. Moving back up the tree, the f3 function finally has its left side answer of 1, so now it executes its right side. calling F1, which immediately returns a 1. Combining the 1 from F2 and the 1 from its own F1 branch, F3 confidently bubbles up a 2. And finally, we're back at the very top. F of 4 has its left side answer of 2 from the F3 branch. Now it runs its entire right side F2 branch, which, going through the exact same steps, will eventually return a 1. So F of 4 adds the 2 and the 1, returning our ultimate final answer of 3. It's absolutely essential that you mentally map this out. You type horizontal code on your screen, right? It looks like a flat equation reading left to right. But the actual execution is a sprawling vertical tree where those leftmost roots have to grow all the way to the absolute bottom before the right side branches can even think about sprouting. Section 5. Exponential time complexity. So we have our answer, but we've got to talk about the massive hidden cost here. To calculate f of 4, the computer didn't just make 4 calls. It made 9 recursion calls. What starts as a seemingly simple calculation triggers an absolute explosion of redundant background work. Because every single function calls 2 more functions, the tree splits bidirectionally, essentially doubling its size at nearly every level. At level 1, 1 call. Level 2, 2 calls. Level 3, 4 calls. Level 4, 8 calls. Seriously, imagine asking the computer for the 50th Fibonacci number this way. You are making 50 calls. You are making literally trillions of calls. This doubling effect means our simple Fibonacci code runs in near exponential O of 2 to the n time complexity. It's technically slightly less than strict 2 to the power of n because one branch is a bit shorter than the other, but for all practical purposes, it acts like a massive exponential curve. It's wildly inefficient because the computer is just calculating f of 2 over and over and over again on different branches, completely forgetting that it already solved it 5 milliseconds ago. So, we know we have to optimize this if we want our programs to survive. The real question is, if multiple recursion creates this massive, slow O of 2 to the n tree, how can we cleverly trim these branches down using dynamic programming? How do we rescue our code from this exponential nightmare? Well, if the problem is redundant calculations, the solution is teaching our computer to remember past answers. But that is a brilliant topic for another explainer. For now, you know exactly how multiple recursion works under the hood. Keep practicing mapping that code out vertically, and I'll see you next time.